Good morning, sir. Myself Chandrika. I am from ECE A section. Today's my topic is chain growth and step growth polymerization. Contents: definition of polymerization, chain growth polymerization, step growth polymerization, applications, conclusion. Definition of the polymerization. Polymerization is a process through which a large number of monomer molecules react together to form a polymer. The macromolecules produced from a polymerization may have a linear or branched structure. They can also assume the shape of a complex three-dimensional network. There exist several categories of polymerization reactions. The most important ones of the step growth polymerization and chain growth polymerization. Both fall under the category of addition polymerization. Polymerization, there are two types: step growth and chain growth. Step growth also divided into two types: poly addition and poly condensation. And chain growth polymerization also divided into four types: radical polymerization, cationic polymerization, anionic polymerization, coordinative polymerization. Chain growth polymerization. Chain growth polymerization or chain growth polymerization is a polymerization technique where monomer molecules add onto the active site on a growing polymer chain one at a time. There are limited number of these activity sites at any moment during the polymerization, which gives the method its key characteristics. Chain growth polymerization involves into three types. First, the initiation. An active species is a one star is formed by some decomposition of an initiator molecule. Second, propagation. The initiator fragment reacts with a monomer M to begin the conversion the polymer. The center of activity is retained in the adduct. Monomers continue to add in the same way until polymers Pi star are formed with the degree of polymerization I. Termination. By some reaction generally involving two monopolymers containing active centers to grow, the center is deactivated, resulting in dead polymer. Chain initiation step, chain propagation step, chain terminating step. R single bond, O single bond, O single bond are gives rise to 2 or O. R O gives rise to C double bond C, gives rise to R single bond, O single bond, C single bond, C dot. Lewis dot. Chain propagating step. R single bond O, O single bond C, single bond C gives rise to C double bond C, gives rise to R single bond O single bond C single bond, C single bond, C single bond, Lewis dot. R single bond O single bond carbon, single bond carbon, single bond carbon, Lewis dot. React with carbon double bond carbon, gives rise to R single bond O single bond, O single bond, try C single bond C and C single bond C, Lewis dot. Chain terminating step. R single bond O single bond, C single bond C. In between the C single bond C and C single bond C, Lewis dot single C single bond, C single bond in bracket of C single bond, C single bond, C single bond, O single bond R. The reactants gives rise to R single bond, O single bond, C 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 single bond in between of C single bond, C single bond, O single bond, R single bond. Step growth polymerization. In polymer chemistry, step growth polymerization refers to a type of polymerization mechanism in which bifunctional or multifunctional monomers react to form first dimers. When trimers, longer oligomers, and eventually long chain polymers, many naturally occurring and some synthetic polymers are produced by step growth polymerization. Examples: polyesters, polyamides, etherins, etc. due to the nature of polymerization mechanism is a high extent of reaction required to achieve high molecular weight. The easiest way to visualize the mechanism of step growth polymerization is a group of people reaching out to hold their hands to form a human chain. Each person has two hands equals to reactive sites. There are also possibility to have more than two reactive sites on a monomer. In this case, branched polymers produced take place. Step growth polymerization. Adipolychloride, hexamethylene diamine, nylon 66. Application. Chain growth applications. First, plastic. It is used to produce polyethylene, polypropylene, polystyrene and PVC. Polyvinyl chloride, which are essential for packaging, construction and consumer goods. Rubber industry. Synthetic rubber such as polybutadiene and styrene butadiene rubber SBR is made through a chain growth polymerization helping in tire manufacturing. Step growth polymerization. Engineering plastics. Polycarbonate is used for bulletproof glass and electronic components. Fiber. Nylon and polystyrene are essential for fabrics, carpets and industrial ropes. Coatings and adhesives. Epoxy resins and polyurethanes are widely used into construction and automotive sectors. Conclusion. Both methods offer valuable approaches to polymer synthesis. Chain growth polymerization is ideal for producing well-defined polymer structures quickly, while step growth polymerization allows for greater control over the formation of complex polymer architectures. Understanding their differences help in selecting the appropriate technique for specific material applications, including plastics, fibers, and coatings. Thank you, sir.